Welcome everybody. I just wanted to give you a quick lab view of what we talked about in class the other day. So we talked about when you measure, this is your positive, long line here, right? And short line, negative, red, black. That if you measure the voltage here, you all agreed that that would be the same voltage as your battery or whatever. So this source is a source that I have that is 3.1 volts. And then I said, well, what if you measure here? It's going to be 3.1 volts. And most people said yes. And when I got to here, some people weren't sure anymore if it's still 3.1 volts. And then out here, is it still 3.1 volts? So I said the answer, you can trust me, is all across this whole thing. Is like one, because these are all wires, and we're assuming perfect wires. All of these are going to give you the same voltage. So in this circuit, you could also actually solve for some stuff in here if we know that the current will divide up through these different wires. Because if it's flowing, the current's flowing along like a river, it's going to divide up through the different wires in the circuit as it splits. Anytime you see a split, like in a river, it flows. Some of it's going to go here, some of it's going to go there. And then again, same thing, split. So that's the definition of parallel, when you have a split, okay? When the two things split, that's going to be a parallel. So in a parallel situation, you always use this equation for your total resistance. We worked some very complex ones on the Friday before spring break. And then we want to remember, once again, that the voltage remains the same across each resistor. So we're going to go ahead and prove that, okay? So I set up this circuit ahead of time. Here we have a squiggly version of what you saw on paper. So what we have here is, this is my source. It's going to the first resistor right there. Okay, and then parallel, it's going to the next resistor right here. And then parallel again, it's going to the next resistor right here. Okay, so I'm going to measure each one of the resistors, voltage across each one of the resistors. So I'm going to turn this and move this up just a little bit more so I can get everything in view. Try and get everything in view where you can still see it. Okay, that looks pretty good. So I'm going to turn this dial to the, on this particular meter, this V with the line and dashes there, that is DC, okay? So I'm going to turn it to DC volts, and I'm assuming that I should have somewhere around 3, so I'm going to go ahead and turn it up to the 6. And that should give me the same voltage here, which is coming off the source of the battery, which isn't on. Now it's on. Okay, so I got the 3.16, and then across the resistor, 3.16. I can come across here at any point, 3.16. I can go here on the wire, 3.16, and then I can go, let me go around the other way so that the cord doesn't get in your view. There you go, 3.16, here, 3.16. So the voltage remained the same across this entire thing. Now I'm going to set up a really simple series circuit, and I want to measure the voltage drop, what we call the voltage drop across the resistor. So I'm going to turn this off, and I'm going to disconnect these. And as you can see, maybe visually, sometimes you have a hard time clipping multiple resistors, but what we did there, we could have actually just clipped a bunch of resistors straight across in parallel. Would have been the same thing without adding the extra wire in there. Okay, so let's set up a quick series circuit with 2 resistors in the series. Okay, we're going to need at least one more wire here. These are really slippery, by the way. Okay, and I'll put another one. And this is the same resistor, so these are the 3,300 ohm resistors. So this is the diagram of what I'm setting up. I'm setting up a series circuit the current remains the same in the whole loop. Let's get rid of the excess wires. So as you go around the loop, the current, because this is the positive, current always goes this way in a standard current, okay? So as you go around the loop, there's no place else for the current to go. It can't escape. So you know the current remains the same. And that in order to solve for the resistance in this setup, for the total resistance, you solve by simply adding the two resistor values together. So we put the two in line, and we're going to see that we have the same voltage here at the 2 points coming back to the battery, but as we measure across each one of these, we'll see that the voltage is different. The voltage is dropping across each one of these. And then we'll be doing, we'll come back and we'll do some actual problems where we solve that as well. Okay, there it is, right? So we leave positive, it goes through the first resistor, through the next resistor, and back to the negative. I'm going to go ahead and turn it on. We're going to measure the voltage, just like we did last time, at these 2 points first. This is coming right off the battery, these two guys. Oh, it would help for you to see. Sorry, I forget that you guys can only see what I show you. Okay, so here we are. This is coming right off of the source. The source is turned on. And I'm touching there, I'm touching there. I still have the 3.16 or 3.17 if you round it up, or you know, you can pick on me about the number. Okay, so now the interesting thing is, as you move it and you're just measuring across one resistor, wow, that number looks like about half. Interesting. So it looks like the voltage drop is half of the total resistance. I'm sorry, half of the total voltage that we have at the source. Okay, so let's take a quick look at this one. And switch it there. And we have half again. So that's very interesting, right? We have a voltage drop across each of these resistors that if you add up the voltage, it would equal the total volts of the source itself. So that's it for today. I'm glad you guys stopped in to take a look at this, and I hope that you join me for the next video where we actually talk about how to solve for voltage drops across a certain resistor and how to solve for the current maybe in a particular leg of the wire or something when we do actual parallel circuits. Thanks, you guys have a great day.